Welcome back to our discussion. Now that we've explored the rocky terrestrial planets, it's time to give some attention to the smaller rocky bodies in our solar system, the asteroids. So what are asteroids? Well, essentially that, smaller rocky bodies that orbit the Sun between Mars and Jupiter. How did they get there? Well, you might recall when we discussed the formation of the solar system that we described how smaller particles stuck together, and these particles eventually became planetesimals. These larger planetesimals would collide together and form the terrestrial worlds. Well, simply put, asteroids are leftover rocky planetesimals that never formed a planet. Why didn't they form a planet? Well, we'll return to that question in just a few minutes. But for now, understand that these asteroids are of varying sizes. Some are quite small, but some may be even several hundred miles in size, in diameter. So we have a wide variety of objects with which to study. They may not seem as interesting or exciting as the terrestrial worlds, but they still hold important clues to not only the formation of the solar system, but how things have changed over time. Now there's plenty of room between them. We don't have to worry about trying to dodge them, and we send our spacecraft out to visit them. And frankly, even if we added them all together, they would not form a very large body. It would be much smaller than any of the terrestrial worlds. So how do we find asteroids? Well, the traditional method involved taking pictures of the sky, perhaps exposing our camera for 10, 20, 30 minutes as we slowly track the sky, watching carefully to see if as we're exposing that picture, an object is moving through the field of view. This would betray its motion around the Sun, and often many asteroids were found this way. Some may require that we go back after a few nights and take several pictures and look for an object again that has moved a small amount from picture to picture. Well, once we have the motion of the object, astronomers can begin to piece together an orbit of the object around the Sun. And once we have the orbits, there's a mathematical law that tells us how far away the asteroid would need to be from the Sun to orbit at that distance and take that orbital period. Well, once we have the distance and we look at the brightness of the object, we can get a first rough approximation of its size. So here already we see just some very simple observations can begin to tell us a little bit about the asteroids. And in this way, again, we've cataloged thousands of these objects, some large, some small, some on varying orbits of varying distances. Interestingly, in recent years, astronomers have actually found some asteroids that have small moons going around them. Why is this interesting to us? Well, because by carefully tracking the motion of the moons around the asteroid, once again measuring the distance and the period, we can learn a lot more about the larger body, the asteroid there. We can actually determine its mass based on the law of gravity. Well, once we have the mass, if we are able to get a rough idea of its volume, we can determine the density of the body. And in this way, astronomers have found that some asteroids are quite dense, solid rock, so to speak, but others are not. They're much lower density, almost like a very porous rock, or perhaps in a few cases, even almost like a pile of rubble floating through space. So a very interesting way to begin to, again, understand and determine some of the properties of asteroids. Now, on occasion, you may hear about an asteroid that's approaching Earth, and of course we may be concerned about that, and rightly so. Well, it's true, some asteroids' orbits do bring them near Earth, and so we simply call them near-Earth asteroids. Here we've got a couple of images that were taken, not so much visually, but with radar of objects that did approach Earth. And as time has gone on, we have begun to discover that a number of objects do approach Earth. Now you don't have to worry, there's no large objects going to crash into Earth anytime soon, but we are becoming much more aware of a number of smaller ones that have approached, well, approximately the distance of the Moon, some even a little closer than that. So we'll come back to that story in just a few minutes. But the point is, we're more aware now that there are a few more of these near-Earth asteroids coming near Earth. So back to the asteroids' size and nature. I mentioned that they're irregularly shaped. Why is that? Why aren't they a nice spherical shape like the larger planets? Well, for exactly that reason. They simply are not large enough to have enough gravity for gravity to shape them into a nice spherical shape. Here you see a very interesting composite picture of one of the largest, asteroid Vesta, which is several hundreds of miles in diameter, compared to a number of the smaller asteroids that are much less spherical. It becomes apparent that, again, the larger body has just enough gravity to begin to shape it into a roughly spherical form, whereas the smaller ones don't. So really, only the few very large ones are able to form a spherical shape. Let's also go back and finish up that question on why the asteroids didn't form a planet. Well, in a word, it comes down to Jupiter. The most massive planet in the solar system has extremely powerful gravity, and as these asteroids, these planetesimals, were orbiting in the general vicinity, Jupiter's gravity would not allow them to orbit at certain distances from the Sun. I'll give you a simple example. If, for example, an asteroid were to try to orbit at a distance where the time it took the asteroid to orbit was some fraction of the time that it took Jupiter to orbit, Jupiter over time would give that asteroid regular tugs, so to speak, and pull that asteroid out of that particular orbit into one where there was not this relationship between their orbits. And so as a result, Jupiter essentially cleared gaps in the asteroid region, preventing any large planet from forming. Now we think some of the asteroids did grow to a modest size through accretion, as we described in our previous lectures, but the point is they could never all form into one large planet as happened in other areas of the solar system. So really, we can blame Jupiter for the asteroids' presence today. Well, besides Earth-based studies, in recent years we've been very fortunate to be able to send spacecraft to visit some of the asteroids, and you can see a few of those images here. Back in the 1990s, the Near-Earth Asteroid Rendezvous mission was sent, flew past the asteroid Matilda, and then rendezvoused with the asteroid Eros. Here the spacecraft was carefully slowed to the right velocity and direction to go into orbit around Eros. And interestingly, the spacecraft had to actually orbit at a very slow speed because Eros is quite small, has very weak gravity. Well, the spacecraft successfully orbited for approximately a year, essentially mapped the asteroid, showed us a few new things we were not aware of, and then interestingly they chose to gently land the spacecraft on Eros. Again, this was possible because of the very weak gravity. And so the spacecraft actually survived the touchdown onto the asteroid and remained operating for a short time. More recently, NASA has sent the Dawn spacecraft to visit two of the largest asteroids, Ceres and Vesta. The spacecraft was first put into orbit around Vesta in 2012, and then after several years, it left orbit there and headed over towards Ceres. These were two fascinating worlds, and that's exactly why they were selected. Why would you want to go to two different bodies? Well, simply put, because of their difference. It turns out that Ceres is somewhat primitive and icy, whereas Vesta appears to be somewhat more rocky and more evolved. So the comparison here between these two large worlds could tell us a lot about not only their evolution over time, but how the solar system would have changed over time as well. Here you see not only the two larger pictures of the bodies, but on our next slide we're looking here at one of the poles of Vesta, and we see enormous craters on the pole. In the lower right you see a close-up of a crater on Ceres with some very remarkable white spots. These white spots puzzled us for some time. They thought perhaps could they be ice? Could they be some whitish mineral? Turns out now, again, this is helping us to learn more about the interior of Ceres and again how it's changed over time. It turns out that We're starting to kind of move away from the ice explanation more towards the mineral explanation, but there's still much to be learned about these two bodies. Speaking of their interiors, is there any way we could possibly understand what might be happening inside of them? Well, interestingly, we think that some of the larger asteroids were large enough to undergo that process we described previously called differentiation. And you might recall this is where a planet's composition changes because the denser material gradually migrates to the center. The lighter material gradually works its way to the surface. We saw the interior of the terrestrial planets, didn't we? Well, if an asteroid's large enough, when it was young and still somewhat warm inside, this could take place. What would happen, though, if perhaps later in the history of the solar system, this asteroid were to suffer a huge impact? Well, it's possible it could be broken apart, and some of the fragments might be from the surface, while other fragments might be from the interior. And in this way, we could end up with smaller pieces of fragments of this larger asteroid that might be more dense or less dense, more metal composition, more rocky composition. And so that's exactly what we found today. Some asteroids do have a much denser composition, made more of metal, and some a much lower density, a rocky composition. So interesting that this idea appears to be a solid idea that some asteroids would have differentiated, and after their breakup, they would give us then bodies of different density. Well, that leads us into the next part of our discussion regarding meteorites. What's a meteorite? Well, simply put, a meteorite is a very small object, relatively speaking, perhaps a piece of an asteroid from an earlier collision that does intersect Earth. It does find its way to Earth and does fall through our atmosphere and reach the ground. Now, certainly some of the smaller objects are going to burn up in our atmosphere. We would look up in the sky and we'd see a shooting star. It's not a star, but it's a small object burning up in our atmosphere. Others, though, would be large enough to survive the fall, and when an object then strikes the ground and we're able to discover it, we would pick it up and say a meteorite. So again, the terminology here is just that the streak of light we see in the sky is the meteor, but the object we pick up is the meteorite. So why would these be interesting to us? Well, frankly, it gives us the opportunity to literally get our hands on a piece of an asteroid. We can go ahead and study this object very carefully and learn much about its composition, perhaps how it's changed, where it came from, all types of things that might help us understand our solar system. Now, there's numerous types of meteorites, but for our discussion, we're going to keep it very simple and just discuss two major types. Number one, primitive meteorites, and number two, processed meteorites. What's the difference? Well, a primitive meteorite is exactly that. It's a body, an object that has not changed. It appears to have gone unchanged since the beginning of the solar system. A processed body, on the other hand, has undergone some change. Perhaps it was heated, perhaps even melted, perhaps it was struck. Other processes may have affected it. Well, that may destroy some of its original makeup and composition, but if we compare it to the primitive meteorites, we can note the differences and determine exactly what processes it did undergo. So really both are quite valuable for us to study. Here you see an example of some primitive meteorites, and again, these are unchanged since the beginning of the solar system, and as a result are quite valuable. If you look closely, you'll note very small little specks here where the arrows are pointing, showing us some of those very small particles that first began to stick together and form the planetesimals during the accretion process. So once again, scientists can examine this carefully, see what that early particles were made of, how they stuck together, what sizes they were, their composition, and so on and so forth, and get a very good understanding of the early beginning of our solar system. Perhaps one of the most valuable things that the primitive meteorites give us is the opportunity to find the age of the solar system. How is that possible? Well, by careful analysis of the rocks and their composition, we've been able to again find primitive meteorites that have not been altered as old as 4.5 or 4.6 billion years old. These are some of the oldest objects that we have, and they essentially put a limit on the age of our solar system. In contrast, you see now some images of processed meteorites, and again we envision these as fragments of larger bodies that were then struck. The pieces escaped, perhaps went into slightly different orbits, and a few of those found their way to Earth. Some, remember, could have come from the center of a large differentiated asteroid, and they would be much higher density, perhaps metal-type composition. Others, perhaps from an intermediate layer or even the surface of such a body, would then be a lower density type of material. Why are these valuable? Well, I mentioned because even though they've been changed, the changes are accessible to us by comparing with the primitive meteorites. If we have an unchanged example and a changed example, comparison tells us what happened. Was it pressure? Was it temperature? Was it impact? Was it any number of different things that may have happened to the body? This, again, can help us understand much more about the body. So we've had a nice overview of asteroids and even meteorites. Let's go ahead and do a summary. We saw that asteroids, again, were rocky leftover planetesimals from the beginning of the solar system that didn't form a large planet. By finding these different bodies and tracking their orbits, we saw we can find some interesting properties of them, can't we? Once we see the orbit, we determine the distance, we get an idea of the size, and for a few of these now, moons allow us to find their masses and their densities and possibly even speculate on their compositions. Why didn't they form a planet? Well, we saw the culprit there was really Jupiter, wasn't it? We saw that some asteroids can differentiate into a denser core and a lower density surface, and if these were broken apart over long periods, some of those fragments could find their way to Earth as meteorites. We pick up the meteorites and we say, well, this particular one has not been altered. Maybe it's an original piece of that solar nebula, and we can find the age of the solar system. But for those that, again, come from a differentiated body, we can easily see, in comparison, what has changed. What has the body experienced? What has it undergone throughout its life? So both primitive and processed meteorites are quite important. Well, our discussion of asteroids really rounds out then our discussion of the inner solar system. We saw, of course, the larger terrestrial worlds. We learned much about their interiors and their surfaces. And now that we finished up with the smaller asteroids, the smaller rocky bodies, in our next lecture, we'll look forward to exploring the outer solar system, beginning with the Jovian planets.